Hi, this recording will show you how to rehandle indeterminate form of the type 0 times infinity. For example, if we're going to find the limit of x times 1 over x, this is the type where you have 0 times infinity when x approaching 0. But what is actually the limit? The limit of this expression, x times 1 over x is 1, so the answer is 1, although it looks like 0 times infinity. On the other hand, the limit of x goes to 0 plus of square root of x times 1 over x. When x goes to 0, square root of x goes to 0, 1 over x goes to infinity. So you also have the indeterminate form of the type 0 times infinity. However, we know that this is equal to the limit of x approaching 0 from the right. Square root x divided by x is 1 over square root x here. This is equal to 1 over 0 plus, and we know that there is infinity. So 0 times infinity is the indeterminate form. Normally we know 0 times any finite number is 0, but 0 times infinity is indeterminate forms. Sometimes you can convert 0 times infinity to 0 over 0 or infinity over infinity, so that Hopital rule can then be applied. For example, if limit of f of x when x goes to a is equal to 0, and limit of g of x when x goes to a is equal to infinity, and you want to find out the limit of fx times gx when x approaching a, this can be written as limit of fx over 1 over gx when x approaching a. Now this is the form of 0 over 0 indeterminate form. If you write this product as gx over 1 over fx, then this product will become a infinity over infinity form. So you can actually convert 0 times infinity into 0 over 0 form or infinity over infinity form, so that you can apply Hopital's rule. Take for example, example 4, limit of x ln x when x approaching 0 plus. So we know that when x approaching 0, we have x goes to 0. However, the limit of x approaching 0 ln x is negative infinity. So you have a form of 0 infinity form. So if you have forgotten, the graph of ln x here is the graph of ln x. Look like. So graph of ln x, y equal to ln x here. You notice that when x approaching 0 from the right, and then you find that the y goes towards minus infinity. That's why when x approaches 0 from the right, ln x approach minus infinity. So the expression is an indeterminate form, 0 times infinity. Now we can either convert this to 0 over 0 form or infinity over infinity form. So if you convert this into 0 over 0 form, it will look like x over 1 over ln x, or limit x goes to 0 plus infinity over infinity form, which means ln x over 1 over x. So the first one is a 0 over 0 form. The second one is an infinity over infinity form, so that you can apply Hopital's rule. Now however, as you look at the form, you know that the second form is much easier to differentiate. So this is easier differentiation. the differentiation is easier, since differentiation of ln x is easier than differentiation of 1 over ln x. Therefore, we're going to take the second case. So let me rewrite again. So limit of x ln x when x approaching 0 plus is equal to limit of, I'm using the second part where you have infinity over infinity case, and then applying the Hopital's rule now. So we know fx is ln x, gx 1 over x now, so that you have a infinity over infinity case, because limit of x goes to 0 plus fx is minus infinity, and x goes to 0 plus gx is infinity, and therefore you have an infinity over infinity case. And you apply the Hopital's rule, you say that this is equal to limit of x goes to 0 plus differentiation of ln x over differentiation of 1 over x. And recall that differentiation of ln x is 1 over x. Differentiation of 1 over x, which is x power minus 1, is equal to minus 1 over x squared. So apply this. This is equal to limit of x goes to 0 plus 1 over x over minus 1 over x squared. Multiply the denominator and numerator by x squared. That means you multiply by x squared, multiply by x squared. Then you have the limit of x over minus 1. So when x goes to 0 plus, this is equal to 0. So the limit of x ln x when x approaching 0 over 0. Let's look at the graph of x ln x. You can see from here, the graph of y equal x ln x, you see that when x approaching 0 from the right, you notice that the y approaching 0. Let's look at another example. Example 4b. Limit of 1 minus tangent x secant 2x when x approach pi over 4. Notice that this is a situation where you have 0 times infinity. This is because when you look at the limit of x goes to pi over 4, 1 minus tangent x, as x approach pi over 4, tangent x approach 1, and you get 0. On the other hand, as x approaching pi over 4, secant 2x is the same as cosine 1 over cosine 2x. In fact, limit of secant 2x when x approaching pi over 4, cosine 2x will approach 0. So it could be less than 0, could be more than 0. So the limit could be plus or minus infinity. So this is a situation where you have 0 times infinity case. Let's look at the graph of 1 minus tangent x. This is a graph of 1 minus tangent x. You'll see that when x approaching pi over 4, whether it's from the left or from the right, you find that the y, which is 1 minus tangent x, will approach 0. So that is why limit of x goes to pi over 4, 1 minus tangent x is equal to 0. On the other hand, I have a graph of y equals secant 2x. So you notice that when x go to pi over 4 from the right, then the y goes to minus infinity. So we can see from here, limit of x goes to pi over 4 from the right, secant 2x is actually negative infinity. On the other hand, if your x approaching pi over 4 from the left, then you find that your y approach plus infinity. That means limit of x goes to pi over 4 from the left of the function secant 2x is equal to plus infinity. Therefore, the limit of x goes to pi over 4 secant 2x. Therefore, the limit of secant 2x when x approaching pi over 4 doesn't exist. It could be plus infinity, it could be minus infinity. So, we have a case of 0 to infinity case. So, I want to convert this to 0 over 0 case. How do I do that? First, we notice that this is equal to limit of x goes to pi over 4, 1 minus tangent x over 1 over secant 2x. And now we know 1 over secant 2x is cosine 2x here. So this is limit of x goes to pi over 4, 1 minus tangent x cosine 2x. Now this is the case of 0 over 0 now because cosine 2x when x goes to pi over 4 is 0. So you can check that if you let f of x equal to 1 minus tangent x, g of x equal to cosine 2x, then we know that at pi over 4, f of pi over 4 is 1 minus tangent pi over 4, which is 1 minus 1 is equal to 0, and g of pi over 4 is equal to cosine 2 times pi over 4, which is cosine of pi over 2, which is also 0, and both f and g are continuous and differentiable at pi over 4. So all the conditions required by the Hopital's rule are satisfied. So according to the Hopital's rule, this is equal to limit of x go to pi over 4, differentiation of 1 minus tangent x over differentiation of cosine 2x. And if you recall, the differentiation of tangent x is secant square x, and differentiation of cosine 2x is equal to minus 2 sine 2x. So this will become the limit when x approaching pi over 4. On the numerator will be minus secant square x, and the denominator will be minus 2 sine 2x. And when x approaching pi over 4, you can write secant square x as 1 over cosine square x over sine 2x after the negative sign cancel. And this is equal to 1 over 2 cosine square pi over 4, 1 over sine 2 times pi over 4. And this is equal to 2 times square cosine of pi over 4 is square root 2 over 2 when you square it, and sine of pi over 2 is 1. So this will give you 1 over 2 times half times 1 over 1, and this is 1. That means the limit when x approaching pi over 4, 1 minus tangent x secant 2x, although this is the form of 0 times infinity, but the limit is 1. If you look at the graph of 1 minus tangent x secant 2x when x approaching pi over 4, you notice that when x approaching pi over 4, the value of y approach 1. That is the end of this recording.